Okay, we're back with section 8.3, conditional probability, intersection, and independence. And we'll introduce conditional probability and independence with an example. It's a little bit easiest to follow that way. And then we'll move into some examples about tables, like problems 1 through 20 and 59, and then some tree diagram problems, examples, like problems 25 through 26, 29 through 34, 37 through 40, 49 through 51, and 61 and 62. So, what's conditional probability and what's independence? So, suppose, we'll start with an example. Suppose 100 people are surveyed, 72 like chocolate ice cream, 48 like vanilla ice cream, and 38 like both. Right? And so this is the beginning of a Venn diagram. Right? And so our sample space is the 100 people surveyed. We have a little circle for chocolate people, a little circle for vanilla people. Looking at the data, right, 38 like both, so that's 38 in the middle. 34 people like chocolate but not vanilla. 10 people like vanilla but not chocolate. And 18 people don't like either one. Great, so that's the Venn diagram. You know, if we're looking at probabilities, right, suppose one person, one of these 100, is picked at random. What's the probability that this person likes vanilla ice cream? Well, there's 48, right? Probability of vanilla is the number of people who like vanilla divided by the number of people in our sample, in our survey. So that's 48 out of 100 equals 0.48. Great. Slightly different question, though. Of the people who like chocolate ice cream, what's the probability of those people liking vanilla ice cream? So now we're not picking one person at random from the whole 100-person survey. We're going to pick one of these 72 at random. So what's the probability that someone who likes chocolate probability that someone likes vanilla, given that we already know that they like chocolate. What's that? Well, how many people in the chocolate circle like vanilla? 38. How many people are in the chocolate circle total? 72. So 38 out of 72 chocolate likers also like vanilla, and that's 0.53. So what is going on with these two numbers? This is looking at all the people in the survey. 48% of them like vanilla. This is just looking at the people who like chocolate. 53% of them like vanilla. What can you say then about the fact that the probability changed, that it went up? Well, people who like chocolate ice cream are more likely to like vanilla ice cream, and more likely than the general populace. Right. 53% of the people who like chocolate ice cream also like vanilla. 48% of people in general like vanilla. Right. So if you restrict your sample size from the whole 100 to these 72, the probability that you like vanilla goes up. Okay. So this is called a conditional probability because there's a condition. Given that they know that we know they like chocolate, what's the probability of it being vanilla? So this is our notation. P of A, the vertical bar would be given. Probability of A given B. Probability of A given B. And so in the above example, probability of vanilla, given that people like chocolate, is 0.53, right? The probability that someone who likes vanilla, given that we already know that they like chocolate, is 53%. This is the formula, right? If we look at our Venn diagram again, right? How did we calculate that? Well, we have our chocolate and our vanilla. The numbers were 18 outside and 34, 38, and 10 inside. So, probability that someone likes vanilla given that they like chocolate, how did we calculate that? we said, well, we're not interested in everybody. We're just interested in the people who like chocolate. And what percentage of those people like vanilla? And that's these people. So, was the number of people who like chocolate and vanilla, right, the people in this area, divided by the number of people who like chocolate, which is everybody inside the red circle. Now, we can always divide top and bottom of a fraction by the same thing, and that doesn't change anything. So if we divide top and bottom of this fraction by n of s, which is the number of people in the entire sample, right, and that doesn't change anything. Oh, I'm running out of space. And so this thing on top here is the probability of chocolate intersection vanilla. This thing here on the bottom is the probability of chocolate. So the probability of V given C is the probability of the intersection divided by the probability of the thing that comes first, right? Vanilla given chocolate, probability of intersection divided by probability of chocolate. And so I always think of it as how many people are in the vanilla and chocolate as a proportion of everybody who likes chocolate. Okay, so here's another version. 100 people are surveyed, 40 are Twins fans, 25 like blueberry muffins, 10 are both Twins fans and like blueberry muffins. So let T be being a Twin fan, B being a blueberry muffin fan. What's the probability that someone who is a Twins fan also likes blueberry muffins? Right? So given that someone is a Twins fan, what is the probability that they like blueberry muffins? So P of B, comma T. P of B given T. Vertical line is given. So according to our formula, that should be probability of the intersection of being a blueberry fan and a Twins fan divided by the given thing, probability of being a Twins fan. And in this case, 10 people are both Twins fans and like blueberry muffins. 10 out of 100 is 0.1. That's this probability. 40 are Twins fans out of 100, so probability of choosing a Twins fan is 0.4, and so that's 0.25. Okay, so a quarter of Twins fans like blueberry muffins. What about the general populace? Well, what's the probability of being a blueberry muffin fan? Well, there's 25 people who are blueberry muffins fans out of 100. So that's also 0.25. So here, right, if we know someone who's a Twins fan, that doesn't change the probability that they're a blueberry fan, right? It's 25% of Twins fans, 25% of people in general. And so we have a name for this. These are independent. Right? In a sense, they don't really have anything to do with each other, right? Twins fans, blueberry muffin fans, you wouldn't expect one to have much to do with the other. On the other hand, you would expect people who like chocolate ice cream to like vanilla ice cream more than people in general, because people who like chocolate ice cream, they like ice cream. So maybe they would like other flavors of ice cream more than the general populace would. So these are independent. And so what we saw above with the Twins fans, two events are independent means if probability of liking a blueberry muffin, given that you're a Twins fan, is probability of liking blueberry muffins. Right? And the second test for independence is if P of A times P of B equals P of A intersection B. Where does that come from? Where does that second formula come from? Well, P of A given B, right, we're working on this part, is probability of A intersection B over the probability of B. So, if probability of A given B is the same thing as probability of A, right, that's our definition of independence. So if these are independents, then that means that this thing, probability of A intersection B over probability of B equals probability of A. And finally, we get our formula. So that's a test for independence. If you want to test if two things are independent, take the probability of the first times the probability of the second and see if that's the probability of the intersection. So we have two different tests for independence depending on how you want to do that. Okay, so some table examples. So problems 1 through 20 are very much like this. You have a table, you have three events A, B, and C. We're assuming that they're mutually exclusive, which means if A happens, then neither B nor C happens. And likewise for D and E. Okay, so what's the probability of A given a table like this? How do you read a table like this? Well, the probability of A is this number. It's the total in the A column, so 0.24. What's the probability of D? Well, you look along the row for D, it's 0.60. And the probability A intersection D is 0.144. And so that's how you find those things. Now, what's the probability of A given D? Well, that's the probability of A intersection D divided by the probability of D. So it's this number divided by that number. And one way to think about this, of course, is you're looking for the fraction of, it's this number divided by that number. You're looking for the fraction of all D's that are A's. So that's 0.144 over 0.60. Which is 0.24. And probability of D given A is probability of A intersection D over probability of A. And that's looking at this divided by that, 0.144 divided by 0.24. And if you divide that out, that's 0.60. Okay, so note that this is, in fact, the probability of A. And this is the probability of D. So this equals probability of A, so they're independent. And you can test either one, right? You can look at probability of D given A versus probability of D, probability of A given D versus probability of A. If this is the same, if these two are the same, then these two are going to be the same. So you really need to only test one. Okay. And then a similar thing for what's the probability of B. The probability of B is 0.46. Probability of E, that's this row. So probability of E is 0.40. Probability of B intersection E is this number, 0.25. Great, and now we can do some questions about probability of B given E, and that's probability of B intersection E. You just have to memorize these formulas. Probability of E equals B intersection E is 0.25 over probability of E, which is 0.4, and that is 0.625, which does not equal the probability of B, right? The probability of B given E is 0.625, but the probability of B is 0.46. So what is going on here? This is saying if we look at the general populace, 46% of them like B, whatever B is. But if we look at people who like E, 62.5% of them like B. So whoever the E people are, they like B more than the general populace does. What about probability of E given B? Well, this should not be equal to probability of E, right? Because if it did, that would say they're independent, which means that this would have to be equal to probability of B. So probability of the intersection over probability of B. Probability of the intersection is 0.25. Probability of B is 0.46. Well, that's going to be bigger than 50%, isn't it? 0.5435. Does not equal the probability of E. The probability of E is 40%. So 40% of the general populace likes E, but of the people who like B, 54.35% also like E. So B and E are correlated in some way, right? If you like E, you're more likely to like B. If you like B, you're more likely to like E. So they're not independent. Okay. Example 2, an insurance company has found the following probabilities by examining driving records. Right? And we'll call this M1 is driving less than 1,000 miles, M2 driving 10,000 to 15,000, and M3 driving 15,000. We'll call this A, and of course A prime, not A, no accident. So, driving less than 10,000 miles a year and having an accident, are these independent? How do you test if they're independent? Well, test accident, given that you drive less than 10,000 miles a year. So what is that? Well, that's probability of A intersection M1 over probability of M1, and that's 0.05, that's this, divided by 0.2. Where's my notes? Here we go. That's 0.25. Right. What's the probability of getting in an accident overall? That's 0.3. So what we're saying is, of the people who drove less than 10,000 miles a year, they got into accidents at a rate lower than people who drove than people in general, right? 30% of the people in general had accidents, but only 25% of the people who drove less than 10,000 miles a year had accidents. So, not independent. What about M2, driving between 10,000 and 15,000? So, we can say M2 given A is probability of M2 intersection A, because if we're testing these two things for independence, it doesn't matter which one comes first, over probability of A. M2 intersection A is 0.1. Probability of getting into an accident is 0.3. That's 1/3, 0.3333. What's the probability of getting into an accident overall? No, what's the probability of someone having driven between of this group? What's the probability of someone having driven 10,000 to 15,000 miles a year? 0.3. So not equal. So not independent. Right. Of all the people who have accidents, 1/3 of them drove between 10,000 and 15,000 miles a year. That's what this is telling us. But only 3/10 of the people actually drove 10,000 to 15,000 miles a year. These people have accidents. Them two people have accidents at a higher rate than general. What about the third one? Well, we can use our other test for independence for this. Probability of M3 times probability of an accident is 0.3 times 0.5, which is 0.15. Probability of M3 intersection A is this number, so it's also 0.15. And if those two are the same, then they're independent. Of course, that doesn't give us any information about, well, here it just means that the proportion of people who have accidents is the same number, in the general population is the same proportion as people who have accidents who have driven more than 15,000 miles a year. Okay, so 3 ways to test independence, right? You can either calculate A given M1, and then probability of A, or M2 given A, either way, and the probability of M2, or probability of the two events multiplied together, and look at the intersection. Okay, some tree diagram problems. So, 2 cards in succession are drawn from a 52-card deck. What's the probability that both cards are kings if the cards are drawn without replacement? So a tree diagram, you all start at the beginning. What's your first choice? We're drawing 2 cards, and it's either a king or it's not a king. Right? What's the probability of drawing a king? 4 out of 52. What's the probability of not drawing a king? Well, 48 out of 52. And then the second choice, we draw a card and we want to know whether is that a king or not a king. King, not a king. And so this is our tree diagram. Now what's the probability that this card is a king, but the cards are drawn without replacement? So what's happened here is I've taken one king out of the deck, so there's 3 kings left and 51 cards total. And there's 48 cards that are not kings and 51 cards total. Here I've taken one card that's not a king out of the deck, so I still have 4 kings out of the 51 cards that are left, but I only have 47 out of 51 that are not kings. And I want to know what's the probability that both cards are kings. So both cards are kings. This is the only way to get both cards being kings. And how does a tree diagram work? Well, the probability of getting a king and then a king, well, and then, that's the tip off that we want to do some multiplication here. So it's the probability of this times the probability here, which is 3 over 51. You multiply as you go out along the branch. So this is the beginning. These are called branches. King, 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 not king, king, not king, king, drawing a king, not a king, and then not a king. So that's 12 out of 2652. So 0.0045 is the probability that you draw 2 kings at random out of a deck if you choose them without replacement. So less than 1%. Okay, another example. So we have 6 red marbles and 3 blue marbles in it, and you choose 2 marbles in succession without replacement. So that means we're picking one out, putting it aside, picking out another one. If it was with replacement, you pick one out, you look at it, you record what it is, and you put it back in. Okay, so what's the tree diagram look like for this? Again, tree diagram starts with the root, and then your first choice, you can choose a blue marble or a red marble. There are 3 blue marbles out of 9, so 3 out of 9, 6 out of 9. First, your second choice, you can get a blue marble or a red marble, a blue marble or a red marble. Now it's without replacement, so that means we've picked 1 blue marble out, so that means there's 2 blue marbles left out of the 8, and all 6 of the red marbles out of 8. Here we've chosen 1 red one, so there are still the 3 blue ones left, but now only 5 red ones. Probability that the second marble is blue, well, that would be this or that. Right? So you can choose blue and then blue, or red and then blue, and that will give you what the probability, the ways to get a blue marble. So what's the probability second is blue, not in, but is? Well, that's the probability of blue and then blue plus, right? Because it's either this one or that one, and whenever we have an or, that's the addition principle. Probability of red and then blue. So what's probability of blue and blue? 6 out of 72. Right? 3 times 2 over 9 times 8. Plus red and then blue, 6 over 9 times 3 over 8 is 18 over 72. So 24 out of 72, which is 1/3. What's the probability that of drawing 2 red marbles? Well, there's only one way to do that, right? You have to draw the red marble first and then the other red marble. So probability of red and then red. So that's this branch. So that would be 6 over 9 times 5 out of 8. And so 30 over 72, which is 0.4167. Finally, what's the probability of drawing at least 1 blue marble? Well, at least 1 blue marble. How do you do that? So probability at least 1 blue. That could be, well, draw blue and then a blue, or you could draw red and then a blue, or you could draw a blue and then a red. Right? And every time I said or there, that gives me another plus. We already calculated this, probability of blue and blue plus probability of red and blue, that was 0.33. So what's the probability of blue and then red? Well, we don't actually have to look at the tree diagram to do this, right? We started with 3 blue marbles out of 9, and we picked one of them, and that meant left in the box were 6 red marbles out of the 8 that are left. And that's 18 out of 72. So, what's the probability of at least one blue marble? That's this 0.333, which is really 1/3, plus this 18 over 72 that we get here, and so that is 0.5833. Great. And note, of course, that these two things add up to 1, this probability plus this probability. What's the complement of at least one blue? That would be 0 blue, right? And 0 blue means 2 red. So drawing 2 red, drawing at least 1 blue, those are complements, so their probabilities have to add up to 1. Complements are a useful thing to see sometimes. So that was a tree diagram without replacement. Similar one, this is going to give us a truncated tree diagram. We have 2 $1 bills, 1 $5 bills, and 1 $10 bills. And bills are drawn at random without replacement until the $10 bill is drawn. So draw the probability tree. So what are the options here? Well, your first draw could be, well, you could draw the $10 bill, and you've got a 1/4 chance of doing that. Or you could draw one of the you could draw the $5 bill, and you've got a 1/4 chance of that. Or you could draw a $1 bill, and you have a 2/4 chance of that. Great. If you draw the $10 bill, game is over. If you draw the $5 bill, what happens? Well, now there's 3 bills left, right? 2 1s and a 10. On your second choice, you could draw the $10 bill with a 1/3 chance, and then the game comes to an end. Or with a 2/3 chance, you could draw a $1 bill. So now, after you draw the 5 and the 1, then there's still 2 bills left. What could you do? You could draw the $10 bill, and that's a half chance, or you could draw the $1 bill, and that's a half chance there. There's only 2 left at 10 and 1. So, don't know where that went. If you've drawn the 5, the 1, and the 1, you have the last bill you draw is the $10 bill, and there's a 100% chance of that happening. Right? There's only 1 bill left, and 1 out of 1. That's the $10 bill. So, if you draw the $5 bill first, this is all the things that can happen. What about if you draw a $1 bill first? What's the next thing that can happen? Well, your second choice could be the $10 bill. Right? If you draw a $1 bill out, there's 3 left in there, a 1, a 5, and a 10. You could draw the $10 bill, you could draw the $5 bill, that's got a 1/3 chance, or you could draw the other $1 bill, and that's got a 1/3 chance. Great, so if you draw a 1 and a 5, what's left? Well, it's the same thing as you have here. You could draw the $10 bill, there's a half chance of that, or you could draw the $1 bill, and there's a half chance of that. And then if you draw the 1, the 5, and the 1, then you have a 1 out of 1 chance of drawing the $10 bill. What happens if you draw the 1 and then the 1? Well, you could draw the $10 bill, or you could draw the $5 bill, because this is the only 2 left. And if you draw the 1 and then the 1 and then the 5, you're left with the $10 bill. Right? And so it's sort of a truncated thing because you don't have the same number of choices each time, right? This just gives you no choices because the game stops once you draw the 10. Once you draw the 5, you have some choices and some more choices, and it goes out. Okay. So, what's the probability that only 1 bill is drawn? Well, there's only 1 branch that's only got 1 thing on it, right? That's only got 1 leaf on it, and that's this one. So 1 over 4. You've got a 25% chance of just drawing the $10 bill right out, and then you don't draw anymore. What's the probability that the $5 bill, I suppose there should be a little S there, is drawn? Well, what are the paths that involve the $5 bill? Well, you could draw it here. This is 1/4. So probability of drawing the $5 bill. There's this one, which is 1/4. These all get broken down, but if you actually added up all these possibilities, they're all going to be up to 1/4. So there's a 1/4 there. $5 bill. This branch doesn't give you one. Oop, this branch does. So that gives you 2/4 times 1/3, which is 2/12 for this sequence. That gives you a $5 bill. And $1, $1, $10, $1, $1, $5. So 2/4 times 1/3 plus 1/2. Right? And so 1/4 plus 2/12 plus 2/24. I think that's 12/24 overall. 50% chance of drawing the $5 bill, right? You could either quarter the time you draw it right here, or 2/12 of the time you draw it here as the second bill after drawing the 1, or you could draw 1 and then the 2 1s and then the 5, and that's that 2/24. What's the probability that all the bills are drawn? Well, you could draw these 4, 1/4, 2/3, 1/2, 1/1, or 2/4, 1/3, 1/2, 1/1, or 2/4, 1/3, 1/2, 1/1. It's the same set of probabilities, right? 1/4, 2/3, 1/2 times 1, so that'll be 24 on the bottom, 2 on the top. Right. And so that's the probability of drawing 5, 1, 1, 10. Or drawing a 1 and then the 5 and then the 1 and then the 10, or drawing the 1, the 1, the 5, and the 10. And since those all have the same probability of 2/4 times 1/3 times 1/2 times 1, right, which is 2/24, it's 3 times 2/24, 6/24. Quarter of the time, you'll draw half of the